Can you see the slide on chemical reaction engineering? Stop sharing for a while. Okay. Can you see the slide? I'm on autocatalytic reactions.
Yes, miss.
Okay. Have we covered everything on constant volume analysis? Or is there a portion which I haven't yet covered? Which part of constant volume integral analysis have we covered? Have we covered everything up to reversible reactions? As per what I could recall, I gave you already sample problems and I said I will continue with variable volume once I'm done with the sample problems. But since we lack the time, I already shared it in Canvas, the entire slides together with the answers so you can do the exercises on your spare time. And I will continue with variable volume reactions. Is this where we're supposed to continue?
Yes, miss.
Okay. Okay, thank you. Slide 51. Okay. So for this afternoon, we'll continue still with kinetics. The first part we have covered together with sample problems on constant volume batch reactor data. Now we go to variable volume reactions. And since it's already variable volume, we need an equation that will relate how will the volume change in terms of conversion. And that linear relationship between the volume and the conversion of a particular reaction is given by this equation, V equal to V sub O times the quantity 1 plus epsilon A XA. The other two equations that you're seeing here, XA and the T of XA, are all derived from the equation above. So if you already have this in mind, then you have memorized this. There's no need for you to memorize XA being equal to V minus V sub O over V sub O epsilon A. Although this V minus V sub O is actually your change in the volume, which is the final volume minus the initial volume of your system. The differentiated form of XA is this one, wherein you have dXA equal to dV over V sub O epsilon A. Now, we have dV because if you differentiate the variables present in the numerator, V sub O is a constant, so its derivative is 0. So that would only leave you with the derivative of the volume. So you have your dV. These two, V sub O and epsilon A, are constants. So V sub O, the initial volume, and epsilon A is the fractional change in the volume of your system. So the formula is written here, and that's the volume when all of A, reactant A, is 100% converted to the product minus the initial volume. The volume at 0% conversion is actually your V sub O. And of course, this one is V sub O as well. So there are, if you can still recall from your kinetics last year, there are two ways in which you will determine the fractional change in the volume. It is more straightforward if the reaction starts with pure A, where A is your reactant. So meaning you don't have inerts or other contaminants that are not converted into the product present initially in your system. So if it's all pure reactant A, then you need only to subtract the sum of the coefficients of the products for the V of X sub A equal to 1. And the reactants would be for the V sub X sub A equal to 0, and the same thing for the denominator. But if your reactant is not 100% pure and you have some inerts with it, then you really have to go back to stoichiometry, to your stoichiometry rather. That way you will know how much of the product will be produced given the percentage of the reactant present originally or initially in your system. So I hope you can still recall the manner of determining the epsilon A. Now, the key to solving variable volume reaction problems is really determining the correct epsilon A or epsilon sub A. If this is wrong, though you only have to follow a formula in which you're going to plug it in, then everything would be wrong. So start with the correct fractional change in the volume. Now, volume is expressed in terms of the linear equation relating the initial concentration to conversion. Now, in the constant volume reaction, we only have Ca equal to CaO or C sub AO times the quantity 1 minus Xa. We don't have this. But if it's already variable volume reaction, we need to account for the variation in the volume, and it's compensated for this expression that appears in the denominator of the original formula to be used in determining C sub A. So this is the original formula that is not encircled. So you just divide it by 1 plus epsilon A XA. Now the formula you're seeing here for the conversion is just derived from the one that you see on top. And it's the second formula that you can use for determining the degree of conversion for varying volume reactions. So if the system gives you changes in the concentration, epsilon A anyhow can be taken from the stoichiometric equation, then you can use this formula. But if the system gives you changes in the volume, then you will have to use the formula that was shown to you a few seconds ago, this one, because in here you have the change in the volume. So the formula to use in determining conversion depends on what the problem provides you to work on. Now, for a zero order reaction, this is your formula for varying volume reactions. It's all pre-derived. And if I may suggest, you should have your notes. You should have a summary of formulas, important formulas, not only for kinetics, but for your other courses as well. That way you will have easy access for those. Now, don't leave it in your computer, because should anything happen to your computer, then you have nothing left for you to study anymore. Okay, so it's really different when you have the hard copy. Now, for first order, this will be the formula. So this time you will have the change in the volume, delta V. Oftentimes the problem gives you this or allows you to determine this. And for second order reactions, we have this one. Now take note, class, that for the second order reactions, the forms that are in which this formula would be applicable to are the forms that you see here on top. So you either start with a single species to most of that single species, or you have two species, but with the special condition that their initial concentrations are equal. If these two species does not start with or does not have the same or does not have equal concentration, then you cannot use the formula that you have in here. So this will only be limited, this formula is limited for these two scenarios here. So you have actually three ready-made formulas for varying volume reactions from zero order to second order. Now, in our general reference book by Levenspiel, multiple reactions are not anymore covered for variable volume systems. So these variable volume systems is limited only to single stoichiometry system. So meaning only a single chemical reaction or chemical equation is provided. If there are several already, in the case of multiple reactions, it's not anymore covered. Okay, so what is only covered for varying volume reactions are this scenario. Now, we go to reactor design. So in terms of reactor design, we have three ideal reactors in which we're going to base our actual design on, and that's the batch and the two continuous reactors. We did not cover the fixed bed or packed bed reactors and the fluidized bed reactor. Actually, it's still part of the CMO, but considering the bulk of the topic, it's never even in face-to-face session. It could never even be fully covered. So our concentration, we're just on the batch reactor and the two continuous reactors, which are your CSTR and your plug flow or your tubular reactor. Okay, now this, I think if you will have your review, your actual review later after graduation, probably this will be covered. But as per experience, even during my time, it's not covered as well. So it's only until this, any combination of these continuous reactors that's being discussed. Now, uh, reactors where homogeneous reactions are effected can be any of this. So we have the batch, the steady flow reactors, the CSTRs again, and the PFRs. And we have the semi-batch or the unsteady state flow reactor. Again, not fully covered. Okay, we're not discussing this even in our regular course offering. Now we concentrate on the three ideal reactors. Now, in terms of representations, this is how we represent the three ideal reactors. For the batch, it could be a symbol block. You have a tube for the plug flow reactor, and you have the CSTR, the constantly stirred tank heater, of course, with the stirrer. The material balance equation that is being used for the batch system is this. So you have the input equated to the output plus the accumulation plus the rate of disappearance. So all these three should be equated to the input. Now, as to the very basic formula that you are to take note of in terms of the batch reactor, it would be this formula. Because what you have on top are the fundamental formulas where this particular general formula is taken from. So determining the time, the residence time of your system for a certain degree of conversion is solved using this particular formula. Let me just enlarge this one so you can see. Okay, so you in here on the left side upon integration, you will have the T. And on the right side, you have CaO, the initial concentration. And of course, the integral wherein generally you have the rate law written as RA. So this is where you will vary in terms of the form of a particular rate equation that solves for the time of the reaction or for the residence time of your system. Now, the RA depends on your system. So if it's a second order system, this will be second order in form. If it's first order, zero order, or third order, so this is where there's going to be any changes. But as to CaO and DXA, this is really the form of the performance equation. So we call this the performance equation. It allows you to determine the holding time or the residence time for a certain degree of conversion. Okay, so you have that. That's for your batch reactor. You need to integrate for the batch reactor. For the CSTR and for the plug flow, there is this particular special characteristic for the two, which is what we call the space-time and the space velocity. Space-time meaning time. So you have, this is the time required to process one reactor volume of feed measured at specified conditions. So the unit is time. The space velocity tells you how many volumes of that particular reactor could be processed for a given time. And as such, you have the unit per unit time. It tells you of the number of reactor volumes of feed at specified condition which can be treated in this unit time in here. So your tau, the tau is B, the volume of the reactor divided by the volumetric flow rate. So the one that you are seeing here is just telling you that one is just the inverse of another. So space-time is the inverse of space velocity, and same thing with space velocity. But generally, this is your formula in determining the space-time. The volume divided by the volumetric flow rate for your flow reactors. Your flow reactors are your CSTRs and PFRs. Now for the CSTR, you have this particular molar feed rate. So it is initial molar feed rate entering the reactor. And this is the molar flow rate leaving the reactor, which is already partly converted. So your FAO is equal to the volumetric flow rate, VO. So that's the volumetric flow rate here, V sub O times the initial concentration, CaO. Your FA will be your, of course, your VO still, because this is a constant volume system. Whatever enters the system, the same volume leaves. So V sub O and V sub O in here. But this time for FA, you will multiply by the C sub A, the remaining amount of A not converted. Okay, so this is for the FA and this is for the FAO. Our main concern, so if you have, if I will fill my markings here, if you have already, where is that? Taken note, took note of the formula for for your batch reactor, your performance equation for your batch reactor. What is important for the mixed flow reactor is just the same. The performance equation for the mixed flow reactor, where there should not be any, of course, accumulation, because it's a constant volume system. That formula is this. So if you intend to make a summary of formula, so this would be the formula for your mixed flow reactor. It is easier because it needs no integration process. You need not integrate. Only though you need to take note of that this FAO is equal to the initial, rather the volumetric flow rate times the initial concentration. So that's your FAO. So if you change your FAO here to this one, the V over small v sub O will be your tau. And as such, this could be written as well as tau over CaO equal to XA over the rate. And most of the time, it's written as tau equal to CaO XA all over the rate. So again, just like in your batch reactor, this is where you're going to have the change. So depending on what is the rate law appropriate for your given reaction. It has to be known that way you can determine the space-time for your CSTR. Okay, I think it's on the next slide where the general performance equation for the CSTR rather is written. It's here, by the way. Tau equal to CaOXA divided by the rate. Okay, that's it. Okay, that's your performance equation for your CSTR. Now, what about the plug flow? So the plug flow, in terms of how it's to be evaluated, referring to the performance equation, you need to integrate it. So for the plug flow, by the way, so I have written it anyhow there in the other slide. So we just skip this one. And this is the comparison now between the batch and the mixed flow. Okay. Now, by the way, you are allowed to write T, the holding time or the residence time, as tau. And this is for the condition we call constant density system. What is this? What are these systems we consider as constant density systems? So these are liquid phase systems and gas systems wherein it's constant density. So it has to be really specified in the problem. So if it's really stated for your gas system that it is constant density, then you can use interchangeably the T and the tau because they mean the same. This is only true when you have a constant density system. Okay, this particular slide simply compares the performance equation for the batch and the mixed flow. Now for the PFR, so determining the performance equation for the PFR requires that you select a volume element of fluid, and that is where you're going to perform your material balance. And that volume element is delta V. Now, the performance equation for your plug flow reactor is very similar to that of the batch reactor in the sense that you have here on the left side. So on the left side, you either have the V over FAO from the integration of the dV here, integral dV, integrated from 0 to V. So you have that, or it could be the tau over CAO because your FAO is CAO small v sub O. So it could be written as this. And the right side is dXA over the rate expression again. So the only difference of this particular formula with the batch is instead of writing it as tau in here, it's T. Because in the batch, what you have as the performance equation is this. T equal to CAO integral of the conversion with respect to rate. 0 to XA. Okay, that's how we write it in the batch. So in here, we just transfer the CAO in here in the denominator and we change the T to tau because we have a flow system. That's it. But they are exactly the same. The integral is exactly the same. The only difference is the T and the tau. I'm referring for the plug flow and the batch reactor. So what is unique of the three ideal reactors is the CSTR where there's no need for you to integrate. Okay, so as for the performance equation, it could be tau over CAO equal to this for your PFR or this one. Anyway, this and this are just the same or they're just equal. Okay, that's for the PFR. Now, let's proceed. So, for the holding time and the space time, so we have covered this also. Holding time, the residence time, referred to as the time of reaction for your batch system. Space time, the time to process the entire reactor, the entire volume of fluid inside the reactor. So this language is used for flow system. So holding time and space time is the same for constant density system, which I have mentioned a while ago. Okay, now we go to, let me just minimize it. The MFR versus the PFR for first and nth order reactions. These formulas are available in the form of a summary at, I think, chapter 5 of Leven's-Speed. And you have the same formula in tabulated form in your handbook. So for the MFR, you have this, the tau sub m, meaning the space-time for the mixed flow reactor. M for mixed flow, and this is for any nth order reaction. So this one, the rate here is not specified. So it could be K only, it could be KCA, KCA squared, or KCA cube, or KCA-CB, or those things. Now, if you have an nth order reaction, this would be your more generic formula in terms of A. So meaning all the rest of the concentration terms there were all converted in terms of A. That way, you will be able to determine the either the space-time or the conversion, whichever of the two is being asked in the problem. Okay, for the PFR, it's quite complicated. It's actually complicated because of this integration part here. There's really a need for you to integrate in the PFR. This is the same formula for the batch. You only change the tau p here to T for the residence time or the holding time. Okay, for any nth order reaction, this is your formula for the PFR. Now, what about if you have PFRs in series? If you recall, the degree of conversion for any PFRs in series, whether same size or not same in size, could be determined by summing up all the volumes of this PFR and considering only one PFR in lieu of several PFRs in the series. So in here, you have a formula that accounts for the total time, residence time, or shall we say space time of your process liquid, whatever it is, in all your reactors. So that's your tau p. And C sub O is the initial concentration. C is the concentration leaving the nth reactor. This is your general formula. This tau sub P would be the tau sub 1 here, tau sub 2, and tau sub 3. Why? Because we consider this series of PFRs as just one PFR in which the volume is equivalent to the sum of the volumes of these individual PFRs in your series. And this is your formula for that. Okay? Now, if we have PFRs in series and or parallel combination, and we want to determine the degree of conversion for the ith reactor, of course, given the degree of the conversion in the reactor before it, then this would be your formula. You have here the molar feed rate to the first reactor in the series. This is the volume of the ith reactor, Ex, and you have here the rate expression. So you need, however, in here you need the conversion of the reactor before it so that you can determine the conversion in that particular ith reactor. Okay? So this is for the ith reactor in an NPFRs connected in series. Now, you have this also, this formula also, as I have mentioned a while ago, as another interpretation of the thing that if you have n PFRs in series, you can get all their volumes and take the sum of all those volumes and determine the conversion on reactor N, or the last reactor that is. So how would you do that? You use the volume of the entire, of all the reactors, of all the PFRs in your series of reactors, divided by the molar feed rate. It would be 0, of course. You don't have initial conversion in your first PFR, and then this would be the conversion for the end reactor. This is your formula for that. We are allowed to take the sum of the volumes of the individual PFRs in our series. Now, the generalizations and principles related to PFRs are all summed up here and also discussed to you as well as here. So NPFRs in series with a total volume V gives the same conversion as a single PFR of volume V. So for PFRs connected in parallel or in any series parallel combination, a single reactor can be used of volume equal to the total volume of the combination, as long as the composition of the streams that meet are the same. So the concentration of the streams that meet, if you have really a combination of parallel series PFRs, they should be the same or equal. Aside from that, so aside from this particular condition, as long as the composition of the streams that meet are the same, you have another one in here. For PFRs in parallel, the tau or the V over F ratio must be the same for each parallel line. So the tau for the upper reactor, which is in parallel, let's say, with the lower reactor should be the same. So dapat pariho ang ilang processing time. Hindi pwedeng ang isa mas dasig ang isa hinay. So dapat dungan sila mag-process sa volume na ginaproprocess. Now, concentration of the reactant decreases here progressively in this system, series parallel series PFR combination. So progressively, the concentration of your reactant decreases. Of course, it has to decrease because it's being converted in the process. So that's in case of, that's the case rather of the PFRs in series or PFR in series parallel combination. Let's go to MFRs. Equal sized MFRs in series. So I think you know fully well the representations here in terms of concentration, conversion, molar feed rate, and volumetric flow rate. So the concentration and the conversion of the stream leaving a particular reactor is labeled by the number of that reactor. So this leaves reactor 1, so this is C sub 1, X sub 1. This one is C sub 2 X sub 2, and this one is C sub n X sub n, because this is your nth reactor. Well, this one is C sub I X sub I, any ith reactor in your series of MFRs. So that's how we represent it. This is our formula as derived already by Levenspiel. You can have it written in summary together with the much needed formula, especially on reactor design. Okay, it's very seldom, class, that board problems are giving purely kinetics. It's usually kinetics with reactor design to follow. So it's really important that you know how to the formula to use for a particular design of reactor or reactors. So for a first order reaction wherein you have a constant density system, because your epsilon here is 0, this is the formula in determining the space-time for any ith reactor in your MFRs in series. So any of these formulas will do. You can also use this particular formula that gives you the ratio of the concentration from I minus 1 reactor to C sub I being equal to 1 plus K tau sub I. But take note, class, that when you memorize this formula or you take note of this, this is for equal sized MFRs. Okay, this will only work if your MFRs in series are equal in sizes or they have the same volume. Okay, if not, you cannot use this particular formula. That goes with the specific condition here that order should be 1 and it should be constant density system. Now we have this generalizations for equal sized MFRs in series. So for n MFRs in series, the larger the number of n, the closer the behavior of the series to that of a PFR with volume equal to the sum of the volume of the MFRs in series. So the more the number of reactors in your CSTRs in series, the behavior or the degree of conversion of that system of reactors that you have, your MFRs, will be comparable to the behavior or degree of conversion of just a single PFR with volume equal to the sum of the volume of the n MFRs in your series. So a PFR is more efficient than an MFR. You know this for reactions whose rates increase with reactant concentration, which is usually the case, such as any nth order irreversible reaction. We know that as the reactant concentration increases, of course, the reaction rate will also increase. And that is the case for any nth order irreversible reaction. So generally, a PFR is more efficient. More efficient in the sense that the degree of conversion is higher compared to the MFR, given the same time, for giving the two systems the same time to process the volume. Okay, the space-time is the same for all equal-sized MFRs. I think this is self-explanatory. Since they are equal-sized, then their space-time should also be the same. Then in MFRs in series, concentration drops immediately to a low value. There is a drastic decrease in the concentration of your reactant A for MFRs in series. Now, with mixed flow reactors, it is more convenient to develop the necessary equation in terms of concentration. It's primarily because, class, your tau equal to CaOXA over the rate already have CaOXA on top. But if you are more comfortable with conversion, then you can convert the rate expression that you have in the denominator to conversion. That way, your tau now will be fully dependent only on conversion. But this is just as observed and as suggested by the author. Okay. Now, more on that. So the optimum size for two mixed reactors in series is found in general to be dependent on the kinetics of the reaction and on conversion. So meaning, it's really dependent on conversion and the rate expression below, given the formula, this one. So taking from the formula, this is the formula for your mixed flow. This is your kinetics. This is your conversion. This is your kinetics. So the processing time is dependent on this too. Now, when n is equal to 1, for equal size reactors, or rather equal size reactors is the best choice. So if the order of the reaction is 1, then it's best that you design your system to have equal size reactors. Take note of this because this is very important. When the order is greater than 1, the smaller reactor should come first. So it should be first in your series of reactors. If the order is less than 1, the larger reactor should come first. So as to how they should be arranged, which one comes first, the smaller or the bigger? This is in the case of two mixed reactors in series. Okay, this one is for equal size reactors for n equal to 1, and in here already for n greater than 1 and for n less than 1. So if you would be asked which one will come first, the smaller or the bigger reactor, if the order is like this. Okay, now more on the order, or more on the, not the order, but rather determining the concentration on the nth reactor, this time when the order of the reaction is second order. Still constant density. The way it's written here, class, is very different than the way it's written in the text, so I will have to share that with you. That way you could see the actual thing. Let me check. It's the thing that has the dot, dot, dot. Let me check. Second order. I have shown to you this one, and I hope you can still remember it if I'll show it to you again. Second order. Looking for it in the textbook. That way you can see the actual equation. Here it is. So let me share this. Can you see it, class? So determining the concentration in the nth reactor for your n series of MFRs for a second order reaction, constant density would be something like this. The number of square root or radical sign that should appear is equal to the number of MFRs in your series plus 1. This one is not included. Only this. The number of radical sign that you have should be equal to the number of MFRs in your series. This one is not included. The last radical, which is 1 plus 4 C sub O K tau I. Okay, so it cannot be written in our slide the way it's written in here, so I'm showing it to you. Just go back again to your book and check as well on your handbook if you have one formula equivalent to that. Okay, now what about if you have your series MFRs, but this time they are different in sizes? So you have here tau sub I in this case equal to the volume of the first reactor divided by the volumetric flow rate that is being processed by that reactor, equated as well to the initial concentration minus the final concentration divided by the rate. Now, you could see in here, class, that if it's referring to a particular IET reactor, in your MFRs of different sizes in series, you notice that it's really being labeled, the R is being labeled as R1, R2, if it's R2, or in this case, that's RI. Now, do you understand why it's labeled as that? If it's the same rate law, why the need for the rate to be labeled as negative R and then parenthesis 1? And let's say, for example, I'll write it in here so you would understand my question. You have tau sub 2 equal to, let's say I write here, tau sub 1 minus tau sub 2 over this time, I'll write rate 2. Why do you think there's a need to have a subscript 1 here and a subscript 2 here? Are these rate expressions different, or they're just labeled as 2 and here it's just labeled as 1 because we're determining the space-time for reactor 1 and reactor 2? Anybody who knows the reasoning behind why we have this? Are these R1 and negative R parenthesis subscript 1 and negative R parenthesis 2 the same, or they're not the same? It's just the labeling that we have placed. We just specify it para mag-agree na lang din sila. Tau 2 niya siya dapat R2 na din. Tau 1 niya siya so dapat R1 na din. So anybody who knows the reason, who knows whether they are the same or not, we're done with this. Let me check. What do you think, Eugene? Is this R the same?
Yes, Guru, Miss.
Ay,
Dali pa kami, Miss.
the same lang. Sige, be. Si ano, be? Jabe, May. Is this R's the same? Nga, aging label, gid siya 1, hala nyo. Ang isa ya 2. Para lang mag-uniform ang labeling or the same na sila. So Eugene says it's just the same, Miss. Para lang mag-agree ang labeling. Jabe, May, what do you think? Jabe, May, not here. Jabe, May. Oh, Jabe, May is not here. Giselle. What do you think, Giselle? Juliana.
Good evening, ma'am.
Good evening. What do you think? Are they just the same?
Same Guru, miss.
Alam nyo? Sadya. Pauline, are they the same?
Hello, miss. Not sure, pero I think the same, miss.
Hala, sadya. Eh, wala gid ko, hindi gid ko good teacher. They're not the same. They're not the same. Why are they not the same? I'll show you. They're not the same. It's not labeled as, in here it's R1 because, I'll use na lang white ink. This R1, let's say for example, if the order of the reaction is first order, is actually K CA1. What is CA1? Isn't it? It's the concentration. It's the concentration that leaves reactor 1. That's the same concentration inside. Okay? But once you change, if it's, let's say, if it's already tau 2, of course I'll change this one. So this would be now C sub 1 minus C sub 2 because I have here C sub O minus C sub 1 if it's tau 1. So it's the previous minus the final, or the initial minus the final, all over This time I'll write R, and it's 2. The reason why it's 2, it's not because it's 2 here. Although you're right, it's the same rate law because in form they are the same, but it's not the same. It should be C sub 1 minus C sub 2 over K. Let's say first order again, but this time this is Ca2. And Ca2 is the concentration here. So they are really different. They are not two the same thing. This is Ca2. Okay? That is why you could see in here, actually this was, as I think I had it written very wrong here. It should be I. Generally, the rate on the ith reactor, because we're talking about the reciprocal of the space-time on the ith reactor. So take note of that just in case I was not able to emphasize it last year, that the rates written in the performance equation for your MFR changes specifically in the concentration term. But in terms of the form, they are of course the same because we're talking of the same reaction. But as to the concentration that we're trying to follow through in the course of the reaction here, from one tank to another, it's really different. Okay? Sige, I'll proceed now. So in here, you have an example this time of reactors of different types. Okay? Now you have a CSTR, you have a PFR, and another CSTR. Now it could be in this, it may not be in this combination. You may only have this and this, but you have here an example on how to write all performance equations, if you notice, are expressed rather in terms of space-time. So they are all expressed in space-time. Tau 1, tau 2 for that, and this one is tau 3. So the form of the equation changes. So you notice here, in tau 1, it's rate 1. Because, again, this would be first order, this should be KCA1. Or if it's second order, we can square it. Now in here, it's different. This should be KCA3. And this should be squared. The same form, the same rate law, but different concentration. Now in here, for your plug flow reactor, this one in the middle, wherein you are to determine the space-time tau 2, you need to integrate. So it's the same form of the performance equation for the batch reactor. The only difference of this is we're talking about space-time, not just time or residence time. But it's still the same. So if this FO is changed to VOCAO, it would be exactly the same form as that for the batch reactor. Okay? Now, any question? This is how you should write the form. This is the form of the performance equation for this first reactor. This is for the second reactor, and this is for the third reactor. All in terms of space time. Why? Because it measures how fast is it going to process given the degree of conversion. So that's why it's space time that is used. So that you won't have any problem memorizing formulas, memorize in terms of space time, because you have a common denominator for these three: the batch, the CSTR, and the PFR. Okay? For our review, if you notice, I did not include the recycle reactor. Excuse me. That would be discussed in detail na lang in your actual review for 5 months. Okay? That is if it will be covered there. Okay? As per my experience, it was not covered in our time. But maybe in your time, it will be covered already. The only combinations of reactors were covered. Now, it's 6:28 in my time. We'll have a 10-minute breather. We'll continue at 6:38 with heat and mass transfer. Okay, I will just have this pause, and after 10 minutes, come back. We will continue. So we are now on heat and mass transfer, and I've labeled this part of the review for unit operations as part 1, because part 2 will be for separation processes already. So in here, I have divided the topics into evaporation, heat exchangers, crystallization, and drying. So we go first to evaporation. So as you learned in your third year, evaporation is the process of concentrating the feed by evaporating a portion of the liquid that is present on it. But it does not have to come to the point wherein precipitation of the solids occur already. Because once precipitation occurs, it's not anymore evaporation, but rather it's now a different topic, which is crystallization. Oftentimes, in evaporation, we are concerned with the final product, which is the concentrated liquid, or the L. But there are processes in evaporation wherein it's not the concentrated part, which is the desired product, but rather the vapor. And that in those cases are in the case of water treatment and desalination. So in the case of water treatment and desalination, it's not the concentrated part of the feed that we're interested in, but rather it is the vapor. So simply put, when we speak of evaporation, the primary objective is in concentrating the solution. Now, in here, we have the performance measures as well, and we have the capacity of the unit or your evaporator, and that is measured in terms of kilograms water vaporized or evaporated per unit time. So that speaks of the capacity of your evaporator. Now, when you speak of economy as its performance measure, how much water was vaporized per unit amount of steam used. So in this case, it's oftentimes expressed in kilograms water evaporated per kilogram steam used. That is for your economy. Another performance measure also of the evaporator is the steam consumption, which has really something to do with the cost of the operation. So the kilogram of steam used per hour of operation. Now we can connect steam consumption to capacity and economy based on this formula in here. So the steam consumption is equal to the capacity, the water evaporated per unit time, divided by the economy, which is the kilograms of water evaporated per kilogram steam used. In the process, you'll come up with the unit, which is kilogram of steam per hour. So that would be your steam consumption already. Now, as to the nomenclature of the diagram for the evaporator, it could be a simple block or it could be something like this. So the T sub F is the temperature of the cold feed that is fed to your evaporator. The T is the superheated, the temperature of the, by the way class, this should be capital T. It's the temperature of the vapor space equivalent to the saturation temperature at the operating pressure. Now, there are problems that gives you not the temperature of the vapor space, but rather the operating pressure of your evaporator. So all you have to do is go to your steam tables and find the saturation temperature at that indicated operating pressure of your evaporator. That would be then the temperature as well of the superheated vapor. Now, the temperature inside the vapor space and the temperature of your concentrated liquor are the same. So if we have T in here, as represented, it's small t, it should also be small t in here. These two have the same temperature. The concentrated liquor, that's represented as L, and the superheated vapor, which is the V. Now, what particular thing is being used to concentrate the feed? So what is being used in concentrating the feed? That is the steam. And once that steam's energy is already used up, it's referred to as spent steam. And the term used is the condensate, or in some other reference books, it's referred to as the drips. So you may wonder what's the drips? It's actually your spent steam already converted to liquid. So the energy of that was already transferred to the feed to have it concentrated. So this is how we represent our evaporator. Now, concerning evaporation, we have this During's rule. And you have the During's chart in our, we have the During's chart in the cave and Genpo please. And we have it as well, of course, in Paris. So, according to this rule, for every given temperature, the boiling point of the solution is a linear function of the boiling point of the solvent. Now, in your handbook, it's figure 11-124, page 11-115 of the 8th edition already. So I've updated it. This is already the current edition of the handbook. Now, this allows you, the During's chart allows you to determine the corresponding increase in the boiling point of the solution. So your boiling point of your solution will be elevated due to the presence of the solids in it. Now, normally, this boiling point rise or boiling point elevation is negligible, or we just consider it as negligible if the concentration of our feed is less than 10% solids. So if not, then we have to account for the corresponding rise in the boiling point due to the presence of the solids. Now, another thing that would help us simplify the problem of the evaporation problem is when we neglect as well the PPR for solutions in which we have organic colloids. So organic colloids or solutions in which the concentration are less than 10%, it's okay to neglect the boiling point rise. So an example of a During's chart is this one, just for illustration purposes. You have an equivalent of this in your handbook. You have in the horizontal axis the boiling point of pure water, and on the vertical axis the boiling point of your solution. In this During's chart, you have lines and you have curves in which you are to use the corresponding percentage of the solids in your feed. So this one means that there is 0% solids in the feed. For this line, there is 5% solids in the feed, and so on and so forth. It could be a curve, it could be a line. So if the particular concentration of solids in your feed is not really one of the lines as drawn or curves that are drawn in the During's chart, then you can just simply approximate it. The system that is in this particular During chart is for the sodium chloride system. I intentionally place it in here because what you have in your textbook and in the handbook is sodium hydroxide. So this one is for water sodium chloride system. So this is how the behavior of your solution, if you have a certain amount of sodium chloride present in the feed, how will it increase the boiling point? So what you're going to do is simply, you look for the concentration line or curve based on the given in the problem. That is, let's say for example, if it's 25% solid, so that would be this one here, this line here. This one, oh, why it's white. That would be this line, okay, for 25% solids. Now, you're going to determine the boiling point of water at the indicated, the boiling point of pure water at the indicated temperature of your feed. So what should be the boiling point of pure water? And you use that as a basis. Let's say, for example, for the indicated temperature of your feed, the water is going to boil at, let's say, this is boiling point of water. Let's say for the indicated pressure in your feed, this would be the temperature of boiling water. Okay, you go up until you reach this part here, which is corresponding to 25% solids, and you read the corresponding BP of your solution in here. Okay, oftentimes if the pressure or the temperature of the feed is not given to be used here, oftentimes we use the saturation temperature at the indicated operating pressure of the evaporator. Whatever is the operating pressure of your evaporator, get its saturation temperature. That would be the boiling point of pure water at that particular pressure, if it's just pure water. But since in that case, you have a certain amount of solids, then it will of course increase. So this will be the corresponding increase in the temperature of your solution. So from an originally, if it's just water, from an originally 100 degrees Celsius boiling point temperature of solution, if it's just water, you will have it now increase to, let's say, if you're going to read it here, it's around 108. So the BPR will be the difference between 100 and 108. So your boiling point elevation or your boiling point rise is 8 degrees Celsius, because what you're reading here is the boiling point of your solution. So BP of your solution minus the saturation boiling point of your solution is the BPR or the BPE, the boiling point rise. Now, we use the BPR for, as I've mentioned over and over again, if the percentage solids of your feed is greater than 10%, we account for the BPR of our solution. Okay? We check in your book, in your handbook, the corresponding Durings chart for NaOH and for other systems as well. This is just for illustration purposes. I have here the formula in determining the elevation in the boiling point if, of course, the informations are all available based on this particular formula. So let me just decrease this one. I will try to have it projected if you can see, class. Let me know if you can see. Can you see? Can you see the projected slide? If you can see any reaction, anybody who has a microphone. Can you see the projected slide?
No, miss. Ang ano man dyan, pagkakita namon.
Okay. Sige, sige. Can you see? Nag-yes si Earl. You can't see Earl. Sige, sige. I'll go back na lang. Okay, kagamay, so hindi nyo makita. Okay, the M. Okay, let's see. Lain na nga slide. Yes, lain na nga slide. Can project. Anyway, I'm here. So this is another formula that you can use. I found it in my readings on how to determine the boiling point of your solution. So you have, I'll just define the things that you could see in the formula. So you have this lambda subscript VAP. So that's the latent heat of vaporization of water. So this is the value in kilojoule per kilogram, and you have a value here in joule per mole. So that should be placed in here. The universal gas constant that you're going to use is 8.314 joule per mole Kelvin in here. And you have the T prime. The T prime is the boiling point of your solution after the addition of the solids. So what you're going to get here is the boiling point of your solution, and you're simply going to subtract from it the boiling point of pure water, which is T, just like the way we get it from the chart. The difference of the two will give you the BPR or the BPE. Now, the X sub W that you have here is the mole fraction of water in the solution. So if you are given the mole fraction, take note that it's not the mass fraction, it's the mole fraction of water in the solution. If you're given that, then you take the ln of that and equate it to everything that's in here. If you know the boiling point of pure water, then you substitute it in here. The only remaining unknown is the boiling point of your solution. Knowing the boiling point of your solution, that would be the elevation in the boiling point or the BPR. It's already stated in here. Okay? Now, this is another way of determining the boiling point if the system that is not given you is you don't have the available During chart for your system, because let's say you have NaOH water system and ACl water system, all of which have different Durings chart, so they don't have the same Durings chart. So if a system is not the one that you have in your handbook, which has the rinse chart, then you can use this particular formula in determining the boiling point elevation. Okay? Take note of this particular formula. It needs only the mole fraction of water in the solution. Now, we continue. Now, elevation in boiling point for dilute solutions can also be determined using this one. If you could remember this, delta TB, the boiling point elevation is equal to K sub B times the molality, where K sub B is the molar boiling point constant of the solvent, and M is the molality, the number of moles of solute per kilogram of solvent. This would be the corresponding rise in the boiling point. Do you recall this formula? Can you recall this formula? It's given to you, I think, in the topic under colligative properties of solution. The freezing point depression and boiling point elevation. So you can apply it as well in here. Okay? Molality, you need the molality and the molar boiling point constant of your solvent. This one you can get from section 2 of your handbook should your solvent be not water. So your molality will just be simply determined using the formula moles of solute per kilogram of solvent if the solvent is not water. So you can still determine the boiling point elevation. Okay? Now, for water, it's given here, but if it's not water, then you have to go to your section 2 of your handbook to find the K sub B for that. You can still determine the in a simple manner, the boiling point elevation of your solution without really having to go back to the unit operations topic on evaporation. Now, you recall this, we have a simple material balance for evaporators. So we have to add the liquor, the thickened liquor, and the evaporated water, and that should be the same amount as the feed that was, of course, introduced into your evaporator. Your solute balance will be based on the primary assumption that there is no entrainment. So what do we mean with entrainment? That your vapor will not contain any solids or will not contain any solute. I think in the industry, you know already that the evaporator water, if it's being recycled in the boiler, it should have zero solid present on it. If not, your boiler will explode. So that's how important it is that your evaporator unit should not have any entrainment. So in that case, class, you see there's no V here plus YV. It's because there's no entrainment. That's our primary assumption. So you work on these two material balance equations, and we have this energy balance equation. You have the feed multiplied to its enthalpy. You have the steam multiplied to its latent heat of vaporization, and it's equated to the product of the liquor and its enthalpy. Same thing with the vapor and its enthalpy. So we use these three equations for all the problems that we encounter in evaporation. So I have here a sample problem. This is still the simple representation of our evaporator. It's just this one. So we have overall material balance, you have the solute balance, and you have here the energy balance. Now, if the enthalpy of the feed cannot be determined from a source, you can determine the enthalpy of the feed, if you can recall in our discussion, by using the MCP delta T formula. Now, you may wonder, then Miss Ali, what would be the delta T, because we're specifically determining the enthalpy of the feed. What should be the delta there? So there should be what we call as the reference or datum temperature. So if you recall in our discussion, if we're dealing with SI units, your datum temperature is 0. When we're dealing with English units, our datum temperature is 32. So if our system, if you cannot find the enthalpy of the streams for your evaporator for a particular system, there's no available table or graph to get it from, you can use the MCP delta T formula. In all your streams, you can use MCP delta T. The final temperature there in the delta T will be the temperature of your stream, subtract from it the datum temperature. So whatever is the datum temperature used in the feed, that would be the datum temperature that should be used in the thickened liquor. Okay? Review your notes, go back to your notes if you don't have a chart for the enthalpy. In the case of NaOH, since it's the most common system that is used in evaporation problems, then it has an enthalpy diagram where you can get the enthalpy of your liquor or your feed based on its solid content. So there's a diagram for that. So I'm just saying this if there is no diagram where you can get the enthalpy of your liquor or your feed. Okay? Now, you can also have this one. So this one is used for if you don't have the enthalpy of the feed. So you can use that one or you can have this. Okay? Energy balance or enthalpy balance is just the same. Now, we'll continue here. Now, the amount of heat that is transferred to the feed is equal to UA delta T, or UA times the difference between T sub S minus T sub B. Now, you know that U is the overall heat transfer coefficient, and A is the area, the total area of the tubes in the calandria of your evaporator, and T sub S is the saturation temperature of the steam, and T sub B is the boiling point temperature of the solution. So this is the part where the boiling point of the solution is very important. It's taken from the Durin's chart if there is a corresponding boiling point elevation or rise. As for the temperature of the steam, you use the steam tables if it's not given and you are given the pressure of the steam. So you can use the steam tables. As for the A, sometimes it's the one that is being required by the problem, sometimes it's given. But oftentimes, the overall heat transfer area is given. So this is the amount of heat that is supplied to your feed. That way, it is able to vaporize the water content to increase the solids in the thickened liquor. So this is our formula for the Q. This is a standard formula that you need to memorize for evaporation. Now, I will continue. Now, in evaporation, we can also have this one. The heat supplied by the steam is equal to the sensible heat plus the latent heat of vaporization. The Q that is supplied by the steam is equal to ms lambda s actually. Oftentimes, we don't have any problem with this because we can get the lambda s from the steam tables. But it is also equal to the sensible heat. So you have here the sensible heat and the latent heat of vaporization. Oftentimes, all of the evaporation problems allows us to determine the Q based on ms lambda s. Now, as for the CP, in here that you could see in the formula, it's the specific heat of the feed liquor. Just in case it's impossible to determine right away the Q based on this formula. So the CP of the feed liquor is the C sub P in here that is indicated because the multiplier here is the mass of the feed. And the Q sub B is the boiling point of the feed minus this is some reference temperature. Okay? Some reference temperature depending on the set of units that is given in the problem. Now, this is the mass of the vapor, and this is the latent heat of the vapor, the lambda V. Now, this formula will give you the same value as the product of ms delta S. Anyway, everything is defined in here. Lambda S, latent heat of the condensing steam, and lambda V is the latent heat of vaporization of water. Now, for the majority of an evaporation process class, the rate of heat transfer is the controlling factor. And the rate of mass transfer only becomes important when the liquor becomes highly concentrated. So the governing factor in the design is the rate of heat transfer. Secondary na lang ang rate of mass transfer. So it's something that we consider when our liquor becomes concentrated or the solid content of the liquor increases. Now you have this sample problem here. I will not have it discussed anyway. It's single effect, and you have the solution in here. Illustration, and you have the solution. Please read on that anyway. It's shared already to you in Canvas. And another sample problem here. Now I'd like to go to multiple effect evaporation. So this time we capitalize on the energy content of the steam. We just don't discard it right after using it for the first time, but the energy of the steam that was transferred to the feed and is actually the one responsible for the vaporization of that portion of the feed. Now it still has energy. That is why the vapor from that particular unit is being used as the heating fluid of the next. That is in the case of multiple effect evaporation. As you could see in here, you have a triple effect evaporation system, and you could see that the vapor from the first effect heats up the calandria of the second effect. The vapor of the second effect heats up the calandria of the third effect. The product of the first effect is further processed on the second effect to concentrate it further. The product of the second effect is introduced on the third effect to concentrate it further. The final product is this one. So don't mind the subscripts or the representation, because this was just taken from a different source. So the representation are not the way we represent it as discussed in the book and as presented in your handbook. This is just for illustration purposes. This is your feed. And this is your steam. You see this MS1, so that's your steam. This is your condensate 1, or that's the spent steam. This is your condensate 2, and this is your condensate 3. The last vapor from the last effect, of course, goes to the condenser where it is being condensed and recycled again in the system. Okay, so that's multiple effect evaporation system. What about this one? What added formulas do we need to take note of regarding multiple effect evaporation? So let's look into one by one. So in here, when we determine the delta T, it's not as simple as the delta T that we have here if we have a single effect. Okay, I'd like to go back to that so you'll be reminded. This one. The Q. This one. So the delta T that you have here is simply a simple case of the difference of the temperature of the steam minus the temperature of your solution, the boiling point of your solution, that is, whether it's elevated or not. This is our formula for single effect. But if it's multiple effect, it's different already. You have to consider a different formula considering already the summation of the BPRs for each of your effects. So your summation of delta T is equal to this time the difference in the temperature of the steam, that of the feed, and the summation of BPRs. If there's no BPRs, then it would simply be that of the steam minus the feed. Now, temperature of the last effect rather. This is actually, in our case, T sub 3 if we have a third effect, T sub 4 if we have a fourth effect. Okay, so T sub F is the temperature of the last effect, not the feed. I got confused here because it's written as F. Now, the formula in determining the change in the temperature for a particular effect, so let's say this is delta Tx, where X is any effect, the first effect, the second effect, or third effect, will consider this particular formula. It will use the heat transfer coefficients of each of the effects. So you have X, Y, and Z. So this is effect X, and in the numerator, you have the reciprocal of its overall heat transfer coefficient. Then in the denominator, you have the sum of the reciprocals of all the heat transfer coefficients of your effects, depending on how many you have. The reason why you need to first determine the summation of delta T is because it's needed here in determining the delta T sub X for your particular effect. It's written here in the formula. Okay, anyway, it's defined in here. X is the number of effect and U is the overall heat transfer coefficient. Now, last year you were given a, excuse me, I think if I'm not mistaken, a 13-step process in solving multiple effect evaporation problems. And there's a time and there's a particular step in there in which you need to go back or redo your calculation because the computed, let's say the computed volume or the computed mean area deviates from the individual areas computed deviates from the mean area by more than 10%. So if the individual areas computed for each of your effects will deviate from the mean of these areas by more than 10%, there's a need for you to redo a certain step and have some correction in the process. So the correction is in this form. So how do you correct the delta Tx or the delta T for a particular effect? So it's your original delta T and then the computed area for that particular effect divided by the mean area. So you will have now the corrected or the new delta Tx prime, which of course will lead to new enthalpies. So if you have new enthalpies based on this new delta T, you will have correspondingly a different value for the volumes, a different value for the volumes will result to a different value again for the X, and then so on and so forth until you go again to that particular point wherein you determine the individual areas of your effects. Again, get the average. Hopefully, as suggested in the major reference books that we use, a second trial is sufficient. That will correct already the mean areas, meaning they will not deviate that much from the individual values will not deviate that much from the mean of their values. Sila man mismo ang kuhaan mo mean, dasun sila mismo ay ikumparar mo sa sinanga mean. So if they will not differ from that by more than 10%, then you're okay already. So it's defined in here that your delta T sub X prime is the corrected temperature of effect X should A's vary by more than 10% from A sub N, as I have discussed already or explained. Now, for multiple effect evaporation, we have this primary assumption. Our first primary assumption, I did not place it here, is that the vapors that were evaporated in each effects are equal. The vapors evaporated from each effects are equal. So that's our primary assumption. The second assumption is this, that the amount of heat supplied to each of the effects are equal. So you have Q1 equal to Q2. In the process, we are allowed to equate, of course, what Q1 and Q2 represent as per our formula. So U1A1 delta T1 is equal to U2A2 delta T2. Now, if the areas are equal, if our evaporators are identical, which is often the case, that is why when you are asked to determine the heat transfer area for a multiple effect evaporator system, the answer that you give is the mean of each of the areas which you used in determining the mean. It's because for a multiple effect evaporation system, plus the size of the evaporators most of the time are the same. So if A1 and A2 are equal, then we get to see here that U2 over U1 is just equal to delta T1 over delta T2. This is in the case when we only have a double effect evaporation system. Now, this is very important here, and I need to read this one. So multiple effect evaporators use less heat than single effect evaporators. So for an N effect evaporator, the steam requirement is approximately 1 over N, approximately 1 over N, but requires more heat exchange surface. The heat exchanger surface required is approximately N times for the same output. So for the same output, you need to multiply it N times if you have multiple effect evaporation system. So you capitalized or you use the energy content of your heating fluid, that is your steam, to a greater extent. Okay? You have used it up. You have not discarded the energy content of the steam in the case of single effect evaporation system, wherein you only use it once and then it's discarded already. Now, I'd like to give this to you to read. These are special type of evaporator systems that are written in your handbook. I took this from your handbook. The thermal vapor recompression evaporator and the mechanical vapor recompression. Read them so that you will know what makes them special from the usual evaporator design, or what makes them different. It's in here. And this is your thermal vapor recompression, and this one is your mechanical vapor recompression. So read on those. Anyway, it's also in your handbook. Let me just... So this is a table comparing the steam economies of the evaporator. So you have here, your single effect will have a steam economy of 0.9 to 0.98. The double effect, look at it, it's 1.7 to 2. The triple effect, it's 2.4 to 2.8. The sixth effect, 4.6 to 4.9. The triple effect with TVR, thermal vapor recompression, is 4 to 8. And single effect with mechanical vapor recompression is 10 to 30. Why present this table to you? Because it actually comes out in the in quiz balls. What is the expected steam economy for a triple effect evaporator system? So when you are asked for that, you just get the average of this, 2.4 plus 2.8 divided by 2. If you compare, class, which of these systems that we have here on the left capitalize or uses to the greatest extent the energy content of the steam, it's the single effect mechanical vapor recompression with MVR. So imagine 10 kilograms of water per 30 kilogram of steam. By the way, wait. 10 per 30, so that would be 0.3 only. No, that's small. You're going to ask me, this one is bigger. I stand corrected. It's the triple effect. This one is single effect. The triple effect with TVR capitalizes more on the energy content of the steam. So it's 4 to, by the way, this is 4 to 8. I cannot see properly. Wait, class, it's different when it's projected. This is 4 to 8. I thought this is bar. This is dash. So 10 to 30. This is 10 kilograms of water per kilogram of steam. So this one has a bigger amount of water evaporated per kilogram of steam used. So sa ila tanan, amo ni siya ang pinaka, shall I say, economical based on the amount of water that it vaporizes per kilogram of steam that it is using. Now, the least, of course, is the single effect. 0.90 kilograms of water per kilogram of steam used. Dako pa ang gingamit mo nga steam sa amount sa tubig na gin-evaporate if you're using single effect. Double effect is this one, so an improvement. Triple effect, sixth effect, triple effect with TBR, this one, single effect with NBR. So this one is more economical in the long run. This is also economical, but there is initial capital expenditure for this because imagine in here you have to put up 6 evaporators. This one 3, this one 2, this one with TBR. Okay, 3 with TBR. Okay, so this was not shared to you last year, so please read on this just in case it would be asked of you. Now in here, you're going to click on this. You will be directed to solve problems on multiple effect evaporation system. And it's, like to close this one. And it's also shared to you there. It was already shared to you in Canvas. This multiple effect evaporation problems. Just read on those. Okay? Now, do you have any questions here in evaporators class? If I may suggest initially, though you will be doing it also when you do your review, you make a summary of formula for all your courses, for each of the topics in your courses. You should have your notes. That way, should there be added formulas, you can simply have it inserted. Before then, we used to have these folders with the newsprint also sa amon nga time ng newsprint. That is why when we insert something in our notes, it's easy to have it inserted because our notes are in place in a folder and we are using newsprints and we just insert what we need to have inserted there. We make already a summary of all the things that we need, especially the formulas, and whatever additional thing during the review is added to our learnings, especially the shortcut formula. They will be giving you a lot in the review, then you have it inserted there in your notes. That's how you properly prepare also for the board exam and for your review for now. So you prepare for now. In this case, you have already the formulas. Maybe I missed some, but I think I already wrote here the formulas that you have encountered only in evaporation last year. So should there be added formulas that were not included in here, then you can add it also in your notes. That's how you study. That way, when you solve a problem, you just go back to that set of formulas that you have collated for a particular topic. That way, hindi pala topsy-turvy in your notes. Pag may notes din ka mo yan, mamba na notes din siya. Now, any questions so far in evaporation? We will continue next Wednesday on the rest of the topics here. We still have 3. I don't know how am I going to finish it, but I'll try to finish it with just giving you the fundamentals, the formulas, and the concept. We have exchangers, crystallizers, and dryers next Wednesday. Any questions? I'll stop sharing for now. There's none.